Hi, everybody. So today I'm going to continue talking about oxidation of an alcohol, and then I'm going to move on to a new topic. You have a quiz next Thursday. I'm not going to be able to finish up all of the quiz, all of the material for the quiz at today's lecture, so I'm going to have to slop over into Monday for some last little bits and pieces. Over the weekend, I'll be publishing a study guide where I'm hoping to lay out for you exactly what you're supposed to know and what you're supposed to be able to do for next Thursday's quiz. So I'm going to try to get as much material in for the quiz this morning, but I don't think I'm going to be able to finish all of it, so I'll have to slop over into Monday. So please be on the lookout for the study guide for the quiz next week. Okay, so we were talking about oxidation of an alcohol, and we were talking about the Jones reagent, which is alcohol plus primary or secondary alcohol plus chromium trioxide plus sulfuric acid plus water plus acetone. And we, so let's see, recap of Jones oxidation. We said that if we take a primary alcohol and react that with chromium trioxide, sulfuric acid, water, and acetone, right? That's the Jones reagent. We'll get oxidation of the alcohol, of the primary alcohol, to a carboxylic acid. Whereas if we take a secondary alcohol and expose that to the Jones reagent, so I'm just going to put little quotation marks, same thing, we're going to get a ketone. And if we take a tertiary alcohol and try to do a Jones oxidation on that, we get no reaction. Okay, and we talked about mechanism for the formation of that Jones, for this Jones oxidation product. Okay, and that's where we left it last time, talking about the mechanism of the oxidation of the primary alcohol to a carboxylic acid. So let's continue the thread of that thought. Mechanism for secondary alcohols. Okay, so we start out. So this reaction is going to be similar to what we talked about before, but a lot shorter, mercifully. So there's our alcohol, and here is the chromium trioxide. And we said that the chromium is an electrophile. It's bonded to all of this highly electronegative oxygen atom, and so that chromium atom is starved for electrons. It's electron poor, and so the first step would be the attack of the nucleophilic oxygen on the chromium center to give this intermediate. All right, and then there were some fiddling and diddling with protons. Is that this oxonium ion undergoes deprotonation. That proton goes off into the solution. It's never heard from again. But there are a lot of other protons in the solution, many of them coming from the sulfuric acid that has to be there. One of them goes on this oxygen atom here. So instead of writing all of those steps explicitly, we like to use this symbology here, which means add a proton from, or take away a proton from somewhere and add a proton somewhere else. Or sometimes it's add a proton somewhere and take away a proton from somewhere else. So we like to write that instead of having to take a lot of time to write all the individual steps. So what is going to happen here is the oxygen atom undergoes deprotonation. The chromate ester oxygen undergoes reprotonation. So we have this critical intermediate here of the chromate ester. Okay, and so now it's time for the actual oxidation step, where we have up here on this carbon, we have a hydrogen, and water comes in and it removes this proton. These electrons fall in here, and there's our new carbon-oxygen double bond of the ketone, and this chromium-oxygen bond breaks. So there's our Jones oxidation product of a secondary alcohol. It's a ketone, and we get hydronium ion. Right now, all of the rest of this stuff is all pretty much the inorganic junk we don't really care too much about. And the other product here, I guess, would have the formula CrO3H minus, right? And we said that in by a series of very complicated steps that are not organic chemistry, that this chromium 3 plus eventually becomes, I mean, this thing here eventually becomes chromium 3 plus. Okay, and so now, with the difference in the mechanisms between the primary alcohol and the secondary alcohol, you will recall, is that a primary alcohol now undergoes this series of steps to make an aldehyde, and then that aldehyde is attacked with water. It forms a special kind of alcohol called a geminal diol, and that undergoes yet another cycle of oxidation using this chromium trioxide. Well, but a secondary alcohol doesn't do that, and let's explain why the mechanism comes to a screeching halt here. Okay, so oxidation of primary alcohol versus secondary alcohol. Okay, so for a primary alcohol, we have the primary alcohol, oh dear. Okay, for this primary alcohol, we have all of those steps, and not going to write them all out again, but we have oxidation of the primary alcohol to this aldehyde. Now, this aldehyde reacts with water under acidic conditions, right? We wrote out the mechanism for all these steps last time. And we form a special kind of alcohol called a geminal diol. It's not important what it's called, but that's what it is. And now the carbon atom that bears the OH group, it still has a proton on it. And so this undergoes yet another cycle of Jones oxidation. Yet another cycle of Jones oxidation to make a carboxylic acid. Okay, so now we want to compare all of those events to what happens with a secondary alcohol. All right, so we start out with our secondary alcohol, and we just wrote out the mechanism for how the secondary alcohol is converted to a ketone. Now, the ketone also reacts with water under acidic conditions, right? So I'm not going to write out all of the steps. So just it's all the very same steps. Let's see, let's do this way because we're going to run out of real estate. So now this ketone reacts with water under acidic conditions, and it forms a geminal diol as well. You see how this carbon atom has two OH groups? You see how this carbon atom has two OH groups? So it's all the same steps, but the difference is a primary alcohol has a proton on the carbon with the two OH groups that can be removed to form an oxidation product. This guy, no proton. All of these steps happen, but they don't lead to more oxidation. So right here, this carbon right here, no more H's. This guy here, one H remains, right? And so that's why the primary alcohol goes through two cycles of Jones oxidation to give a carboxylic acid, but a ketone cannot undergo a second cycle of Jones oxidation because the mechanism requires that the carbon atom that is bonded to the OH group have a proton on it, and the ketone just doesn't have a proton on there. Oxidation comes to a screeching halt. Okay, so now, one of the things that is much to be desired with the Jones oxidation is that it would be nice to be able to take a primary alcohol and stop the oxidation at the aldehyde stage, because sometimes going on to the carboxylic acid, that is considered an evil. We don't necessarily want a carboxylic acid. Maybe we want an aldehyde. So this is possible, but it doesn't involve the Jones reagent anymore. It involves a specialty kind of reagent called pyridinium chlorochromate, or PCC. PCC, pyridinium chlorochromate. PCC converts a primary alcohol to an aldehyde, and the reaction stops there. It doesn't go on to make a carboxylic acid, and the reason for that is because there's no water present when we use this PCC. So if we go back to this previous slide, we see that the primary alcohol goes to an aldehyde, and then it reacts with water and acid to form this, this intermediate here that goes on to form the carboxylic acid. But when we run the reaction using the specialty reagent called pyridinium chlorochromate, PCC, it's done under anhydrous conditions. There is no water, so that the second round of oxidation can't happen. So the primary alcohol is converted to an aldehyde. And also the secondary alcohol, that just is the very same thing as the Jones reagent. It converts the secondary alcohol to a ketone. So this PCC stuff, that's pyridinium chlorochromate. So we take pyridine, react that with HCl, and we get this pyridinium chlorochromate. whoops, we also have chromic acid. Pyridinium chlorochromate, which is this species here, right? And this is a negatively charged ion. Okay, so this specialty reagent, PCC, that halts the oxidation of the primary alcohol at the aldehyde stage. Okay, so that's very nice. So let's do a problem, shall we? Okay, so if I were to take this guy, and react him with excess chromium trioxide, CH204, water, and acetone. So draw the structure of the product. And if I were to take this very same alcohol and react him with PCC, sometimes with PCC, you see CH2Cl2, that's just the solvent. But sometimes you see that it's kind of confusing. What exactly is that doing? But it's just the solvent. Okay, draw the structure of the product. Draw the structure of the product here. All right, so Jones oxidation takes a primary alcohol and converts it to a carboxylic acid. It takes a secondary alcohol and converts that to a ketone, and tertiary alcohol is inert toward Jones oxidation. So here's a primary alcohol, this guy here, right? That's a primary alcohol. This guy here, well, you know, I should really have the arrow like that. This guy here, what kind of alcohol is he? He's a secondary alcohol. This alcohol here, what is he? That's a tertiary alcohol. That's a secondary alcohol. So with PCC, the primary alcohol is oxidized to a carboxylic acid. The tertiary alcohol is inert, so nothing happens to it. And the secondary alcohol is oxidized up to the ketone. So that would be the product of the Jones oxidation of this triol. PCC does exactly the same thing that Jones does, except with a primary alcohol is oxidized to an aldehyde. And we just explained how it doesn't go through a second cycle of oxidation. Oh, shoot. I put that guy in the wrong carbon. Let's try again. So that becomes a carboxylic. Sorry. Oh, dear. Try again. Okay, get it right this time. That becomes an aldehyde. Tertiary alcohol, nothing happens. Secondary alcohol is oxidized to an aldehyde. Okay. Okay, so that's the difference between these two reagents. Okay, so now let me ask you a question. So this Jones oxidation with Jones oxidation and PCC, those are all very nice reactions and everything. But somebody here tell me in the chat, why would we want to find an alternative to Jones oxidation? Jones oxidation works great, but it is hardly our first choice when it comes to oxidizing an alcohol. Anyone tell me why? What's so bad? What's so wrong with Jones oxidation? I'll give you a little clue. You have to be woke to think of the answer. Why are we looking for an alternative to Jones oxidation, right? You won't know the answer unless you're woke. Nope. Let's try again. Anybody woke out there? No. Chromium. Chromium is a toxic waste disposal nightmare. Ever heard of the movie Aaron Brockovich? Right? This movie was all about the release of chromium-6. This was all about the release of the Jones reagent into the drinking water of a town. Yeah, so that's why we don't want to use the Jones oxidation, because chromium is a toxic waste disposal nightmare. Okay, so I'm going to do a little demo for you here. I don't like to do demos in the lecture because a lot of the stuff that we deal with in organic chemistry is smelly and dangerous. So better put on my gloves here. I'm going to do a Jones oxidation just for fun. I'm going to create a lot of toxic chromium waste. But for you guys, I love you guys. No environmental devastation is too much or too little for you. Okay, so what's the Jones oxidation recipe? First thing we need is the alcohol, right? Moonshine, right? There's the alcohol. What else do we need for Jones oxidation? The chromium trioxide. And so you see this orange stuff here? That's the chromium trioxide. It's orange. What else do we need for Jones oxidation? Sulfuric acid. I don't know if you can read the label, but this is the sulfuric acid. Okay, so let's see a Jones oxidation. Okay, so let's get our moonshine. Oh dear. Boop. Gloop, 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 gloop. A little early to take swigs out of a bottle of moonshine. All right, so there's our moonshine. There's our alcohol. Go in there. Okay, that looks good. Okay, so there's our alcohol. And now our chromium trioxide, which is this orange stuff. So this is orange. I'm going to pour this into the alcohol. Nothing happened, right? The orange solution stayed orange. Nothing happened. Okay, that's because I'm missing something. I'm missing the sulfuric acid. So now this is where the magic happens, right? And I want you to observe what happens to that orange solution. Now, if I were doing this in the lab, I would be measuring everything, but you know, that's not how I roll. So let's just pour in some sulfuric acid, see what happens. Oh, you see how it turned color? Yeah, and it's supposed to be green. That's the chromium 3+. Woo, and this beaker is wicked hot. This is a very exothermic reaction. You see how that how the solution has turned from orange and it's kind of a blue, it's kind of like a blue-green color. It's actually quite pretty. So that is the chromium 3+, which is the inorganic metal ion that is formed in the Jones oxidation. But now this beaker here, this is still hot. Oh my God, it's wicked hot. But now this beaker here is now a toxic waste disposal nightmare. Okay, so that's a Jones oxidation. Let's put all the stuff away. And we see that that is, we saw that color change. All right, so let me see if I can show you. I think maybe I have some pretty pictures, some additional pretty pictures to show you about Jones oxidation before we leave that. Let's see, do I? Yeah. Let me ask you a question. Don't answer in the chat. Anyone here ever been pulled over by law enforcement on the suspicion of drunk driving, and anyone had a breathalyzer test administered? Yeah, don't answer in the chat and just answer silently to yourself. Well, here we see a Minneapolis policewoman administering a chromic acid oxidation breathalyzer test to an individual. Now, I don't like to judge anyone based on how they look, but this dude here, he looks like he's guilty of something. So anyway, in the breathalyzer, there's a little tube of Jones reagent that is orange, and the subject is blowing into the breathalyzer. And if there is alcohol in his breath, that is going to change that orange solution into a green color, and he's busted. So the Jones oxidation chemistry is has this practical application in law enforcement. It's one of the breathalyzer is based on its chemistry. All right. So we like Jones oxidation. It works very well, but we don't like chromium. So there are greener methods of oxidation of an alcohol, and that's what I want to talk to you about now. IBX. IBX. Quote unquote green method of oxidation of an alcohol. Okay. And the overall reaction is going to be the reaction of IBX, iodobenzoic acid, and this IBX stuff, it has a hypervalent, so this is IBX, it has this hypervalent iodine atom, and so that is the oxidizing agent. There is no chromium. Okay, that's IBX, and then we have the alcohol, and the alcohol can be either a primary or a secondary alcohol. So let's make this, just for starters, let's make that primary. And so what happens here, the overall, so that's primary. So the overall reaction here is we get the IBX is converted into this species, and the primary alcohol is oxidized to an aldehyde, right? And it stops there. It doesn't go on to make a carboxylic acid, right? So notice this iodine, it starts life with 1, 2, 3, 4 bonds to oxygen. At the end of the reaction, it only has 2 bonds to oxygen. And we said last time that this is one of the hallmarks of reduction, a decrease in the number of bonds to oxygen. So the alcohol got oxidized. It starts, that carbon atom starts life with 1 bond to oxygen. Now it has 2. The alcohol got oxidized, but the IBX got reduced. All right, and with a secondary alcohol, IBX plus a secondary alcohol, right, that would be secondary. That would be secondary. That ends up a ketone, right? So we have this guy again. All right, so IBX oxidizes a primary alcohol to an aldehyde, just like PCC does. And IBX oxidizes a secondary alcohol to a ketone, just like Jones and PCC do as well. All right, so this is a better, I mean, well, I don't know if it's better, but it is a method of oxidation that doesn't involve the use of toxic heavy metals that are so difficult to dispose of. Okay, so let's go through the mechanism. IBX. All right, so we start out with the IBX and this reacts. So that iodine is obviously the electrophile, right? Because it's extremely electron deficient. Its electrons are being sucked away by all of these oxygen atoms. And so we have the alcohol. And there's that carbon. And that carbon, whether it's primary or secondary, is going to have a hydrogen on it. That's very important. We saw that with PCC and with Jones. All right, and so that nucleophilic oxygen attacks the iodine. And we have an intermediate. Pretty crowded. All right, iodine can do all this because iodine is a huge, huge atom, lots of room for lots of ligands. Okay, so the first, and this iodine has to have a negative charge on it. So the first step, well, that kind of makes sense. The iodine is the electrophile. It's being tugged on by all of this electronegative oxygen. The alcoholic oxygen is the nucleophile, so nucleophile attacks electrophile. Okay, now there is a lot of fiddling and diddling with protons. So this oxonium ion undergoes a deprotonation. Something's missing. Oh, something's missing. This OH group, right? This OH group that was on the iodine, forgot to write it. All right, so now there's a lot of fiddling and diddling with protons. That oxonium ion undergoes a deprotonation. That proton goes off into the solution, but there are a lot of other protons around, and so one of them comes back on this OH2 here. does the 1O have a negative charge? Does the 1O? Now, I'm pretty sure I've drawn this structure correctly now. So there's a positive charge on this oxygen and a negative charge on this iodine. So no other oxygen has a charge on it except this oxonium. All right, fiddling and diddling with protons. So we get okay, don't screw this up. I'm talking to myself here. See this OH group up here at 2 o'clock on the iodine? That's what gets the proton. There's the carbon. That's what is left of the alcohol. So we have an intermediate that looks like that, where we've just played around and diddled around with the protons. And so now we have, now we're here. And so one of the themes that we've seen quite a lot is that water is a leaving group. So this leaves minus H2O. And so we have this guy. Double bond to oxygen over there. Okay, so we're there now. And now last step is this oxygen, this double bonded oxygen atom up here. It grabs this proton. These electrons in this carbon-hydrogen bond collapse in here. So there's our new carbon-oxygen double bond. So the primary alcohol is now going to come out as an aldehyde. The secondary alcohol is now going to come out as a ketone. And these electrons here rush into this iodine. Okay, so here are our final products. This iodine is that. And the aldehyde, and we have the aldehyde or the ketone product up there. Okay, so this is another method of oxidation, and many, in order to not have to use the toxic heavy metals, there have been many other reagents that have been devised that can oxidize an alcohol without having to, use those toxic heavy metals. Bleach, plain old bleach, that has also been used, and it works pretty well in selected cases, and that doesn't have the toxic waste disposal nightmare of chromium. Let's check in on our chromium, because I see it has gotten much prettier. Right, you see it's that nice blue color. All right. Okay, so now I'm going to, now what I'd like to talk about is biological methods of oxidation, because the lucky ones among you The lucky ones among you are going to take biochemistry, and oxidation of alcohols is extremely important in metabolism and in all kinds of biochemical processes. Okay, but you know, there's no IBX inside your body. There's no Jones reagent, or at least there shouldn't be any Jones reagent. So how does nature deal with oxidizing an alcohol? So that's what I want to finish up talking about: oxidation of alcohols. Biological oxidation of alcohols. And the reagent that Mother Nature has devised to oxidize alcohols, this is called nicotinamide adenine dinucleotide, also called NAD+. All right, and I'll show you a picture of that molecule in a second, but let's just go through the overall reaction, where maybe we would take a primary alcohol, okay, so there's our primary alcohol, and the biological oxidant is called NAD+. I'll show you a picture of the molecule in a second, but let's just write down what the overall reaction and the overall mechanism is. This is called NAD+, nicotinamide adenine dinucleotide. And so this R group, this is a complicated, it has a carbohydrate residue and also adenine, which is one of the nitrogenous bases of DNA. And so how this works is that these electrons from the alcohol come down, and now the hydrogen attacks this position of the NAD+. These electrons come in here, and these electrons come in there. And so we get oxidation. We get this species plus this 12 o'clock carbon of the NAD+. It started life with one hydrogen, now it has two. Where did the second one come from? From the alcohol. And this stuff is called NADH, right? And that H is supposed to indicate that, well, at that 12 o'clock carbon, there are now two hydrogens there, and there is no more positive charge. So we see that the alcohol was oxidized and the NAD+ was reduced. This 12 o'clock carbon starts life with one bond to hydrogen. Now it has two. That's one of our hallmarks of reduction. Okay, this guy over here now undergoes a deprotonation, and that primary alcohol has been oxidized to an aldehyde by NAD+. Right, so this is biological oxidation. Now, is there any water in the physiological system? All right, so let me see. What is this question? Yeah, it's called hydride transfer. We're not transferring a proton. We are transferring H minus, right? This H minus, this is functioning as a nucleophile. This is the electrophile. How do I know it's an electrophile? It has the positive charge. But this hydrogen doesn't attack the nitrogen. It attacks this 12 o'clock carbon. So, and then there's a reorganization of the bonds, right? And why does this happen? This is 3 billion years of evolution, right? This is how Mother Nature can deal with chromic acid. And IBX was invented about 15 years ago, right? This is a biological oxidation. Okay, so is there any water in the physiological system? Oh my heavens, yes. You're something like 85% water. Is there any acid in the physiological system? Yes. So that the aldehyde, this aldehyde, in a reaction we've seen before, reacts with water and acid to form that geminal diol, right? We saw this reaction when we were talking about Jones oxidation. And now this is just a special kind of alcohol where that carbon that has the OH group has a hydrogen on it. And now this can enter into another cycle of oxidation with NAD+. So this guy reacts with NAD+ again, right, by this very same mechanism where I'm transferring this hydrogen to that 12 o'clock position of NAD+. And so that alcohol is now converted to a carboxylic acid. And the other product of this reaction would be more NADH. Okay, so this is how Mother Nature oxidizes an alcohol. So we can take, you can take ethanol, which is the alcohol of alcoholic beverages. Moonshine. Right, we take the alcohol of alcoholic beverages, and your body interprets ethanol, ethyl alcohol, as a toxin to be got rid of. So it reacts with NAD+, and it makes this acetaldehyde. And then the acetaldehyde reacts with water and more NAD+, and you end up with acetic acid as the final product. So this is how your body detoxifies alcohol. But oxidation of alcohols is a pretty general reaction biologically. Okay, so let's talk about NAD+ and a secondary alcohol. All right, so here's our secondary alcohol. Right, there's a secondary alcohol. And so here we have some more, here we have that NAD+ again. So that's that NAD+, and we have the very same mechanism operating here. So electrons come down, that carbon atom can't stop there because now the carbon atom is going to have 5 bonds, so that the proton is transferred here. We get this reorganization of bonds. We have this species. Plus that 12 o'clock carbon now has 2 hydrogens on it. This is called NADH. This guy undergoes a deprotonation to make a ketone. And once again, just like we saw with the just like we saw with the Jones reagent with a secondary alcohol, this guy can react with acid and water to form this special kind of alcohol. But once again, there is no hydrogen left on that carbon atom bonded to the OH group. So so a secondary alcohol, it stops at the ketone stage. NAD plus can't oxidize a ketone to anything else because the mechanism requires that the carbon that has the OH group have a proton on it. Okay, so let me see. Let me check out what's going on here in the chat. All right. Let me see if I can scare up a picture of NAD plus. Do I have NAD plus somewhere here? Oh dear. Aha. Yeah, okay, so here is the structure of NAD plus. See this part up here, that's the, okay, this is NADH. And so all of the action is happening here in this red circle, right? That's the product, that's NADH, a nicotinamide adenine dinucleotide. And so that's all of the action is up here at this 12 o'clock carbon. There's that nitrogen atom, and the rest of the molecule that I've illustrated as R. It's this, this is a ribose residue. This is a diphosphate here, also called pyrophosphate. And this is adenine down here. This is one of the bases that we find in DNA. So obviously Mother Nature's Jones reagent, Mother Nature's IBX and PCC is much more complicated than what we find in the lab structurally. And this these carbohydrate residues and these adenine residues, these are there for molecular recognition because NAD plus doesn't operate on an alcohol all by itself. All of these reactions happen in the active site of an enzyme, right? And so, yeah, they happen in the active site of an enzyme. So in effect, NAD plus is a vitamin. It's a coenzyme. It's a cofactor. Okay. So that's biological oxidation. Let's do some problems. So as I said, the lucky ones among you will be taking biochemistry, and I'm sure the professor there will make a big doodah out of NAD and NAD plus and NADH. So this is isocitric acid. This is involved in the citric acid cycle. And when I react that with NAD plus, what is the product? Well, NAD plus is just Mother Nature's Jones reagent. NAD plus is Mother Nature's PCC. So I see an alcohol there, and that is going to be oxidized to a ketone because that's a secondary alcohol. So the product here of this oxidation would be this, and this is called oxalosuccinic acid. So this is a step in the citric acid cycle, the tricarboxylic acid cycle, or the Krebs cycle. It's just the oxidation of that alcohol to a ketone. All right, and the most familiar complex of reactions with NAD+, they involve ethyl alcohol, the alcohol found in alcoholic beverages, right? So we take ethyl alcohol, react that with NAD+, and what happens is the oxidation of the alcohol to acetaldehyde. Here you're drunk. Now, when this accumulates, you're hungover. And the acetaldehyde is also interpreted as a poison by your body. It wants to get rid of it, and so that is oxidized in a second cycle with more NAD+, and this turns into acetic acid. And this acetic acid, this is a very valuable compound in the physiological system. This is not interpreted as a poison whatsoever. This is a building block for all kinds of other biomolecules. So the NAD+ oxidizes the ethyl alcohol to acetaldehyde, and then the acetaldehyde to carboxylic to acetic acid. This is just what Jones reagent would do. Okay, so that ends the lesson concerning the chemistry of the alcohols. I'm going to get into another topic, but before I do that, does anyone have any questions about the material that talked about so far? Right, I would love to answer your questions, but every time I get a question coming through, I just can't stop whatever I'm doing because that's going to interfere mightily with the continuity of the lecture. So I would like to stop here, there, and this other place to entertain questions. But, you know, I see you send me questions. I'm not ignoring you. I just can't just drop everything. Anyone have any questions about anything? I'm about to launch into more different lecture material now. No? Okay. Okay, so our next unit is the chemistry of the epoxides. Next unit is the chemistry of the epoxides. All right, and what is an epoxide? An epoxide is a three-membered ring cyclic ether. All right, and so let's look at some of these. Let's look at some an epoxide. The simplest epoxide would be this guy called ethylene oxide. It is an ether, but that ether oxygen is a part of a three-membered ring. So that's what an epoxide is. This is the simplest epoxide. It's called ethylene oxide, but we can decorate these two carbon atoms with all kinds of other stuff and come up with more complicated and intricate kind of epoxides. So that would be another example of an epoxide. This is called styrene oxide. This is ethylene oxide. This is styrene oxide, where again, it's a three-membered ring cyclic ether. We could imagine cyclohexene oxide, right? Which is once again a three-membered ring cyclic ether, and maybe something like butylene oxide. which could be that. Okay, so those are just some examples of, some simple examples of epoxides that are encountered in the laboratory. Now, there are a whole lot of epoxides in nature, right? So I think I have some pictures of epoxides that we find in nature somewhere, pretty interesting compounds. Yeah, here's one, periplanone B. This is the sex attractant of the cockroach. And so millions and millions of dollars were spent to figure out what the sex attractant of the cockroach is. And so up here in the upper left-hand corner, we see a 3-membered ring cyclic ether. Down here, dangling in the middle of the molecule in this rather unrealistic picture, we see a second 3-membered ring cyclic ether. So the sex attractant of the cockroach has these two epoxides. And you know, this is millions and millions of dollars went into figuring out what this molecule is for practical reasons. Okay, so don't answer in the chat. Let me just ask you a question. Does anyone live in a roach-infested hovel? Right, you go into the kitchen at 2 o'clock in the morning, turn on the lights, and hundreds of roaches scamper away. Anyone living in a situation like that? Yeah, don't answer in the chat, just answer silently to yourself. Well, one of the techniques for reduction in the number of cockroaches is the roach motel. Maybe you've seen that, maybe you've heard of that. It's a little cardboard box, and the floor of the box, which you're supposed to put on the floor, on the countertop, or in your refrigerator, wherever you've seen cockroaches, has a bed of glue. And that glue is impregnated with this synthetically created, lab-created periplanone B. This is the compound that is emitted by the sexually receptive female cockroach. It can be detected in parts per billion concentration by the male cockroach. And so if you put that roach motel down on, on the floor of your kitchen or in your bathroom or on your countertop in the kitchen or your refrigerator, wherever you've seen roaches, and the male cockroaches are attracted to the roach motel, they crawl into the roach motel thinking they're going to find a sexually receptive female, but they get glued and stuck to the floor of the roach motel. And so the strategy there is by reducing the number of breeding males in the population, the overall number of cockroaches goes down. So maybe you've heard of a roach motel, maybe not. Well, and so that millions and millions of dollars were spent into into figuring out what this compound was so that it could be created in a lab so that you could impregnate that roach motel with lab-created periplanone B. So I think this was finally synthesized by Professor Still at Columbia University. An old-fashioned word for these sex attractants, no longer favored, but maybe you've heard of the word pheromone, right? You've heard of pheromone. Well, that's kind of like an old-fashioned word. Now the modern word is a semiochemical. So a pheromone. So this is a pheromone. It's a sex attractant. And there are pheromones for sex, pheromones for food, pheromones for social gatherings. How do you make a pheromone? You take away his pyramid. Get it? Pheromone, Pharaoh, Egypt, pyramids, moan. Okay. So let's look at another epoxide in nature. Oh, this is the juvenile hormone of the mosquito. So this is the molecule that keeps a mosquito an aquatic animal. And it is produced, and when the production of this compound in the mosquito's body stops, now the mosquito undergoes that metamorphosis. It comes out of its larval stage. It emerges as an adult mosquito. It goes off and it bites you, and it gives you malaria and you know, whatever other mosquito-borne Eastern equine encephalitis and whatever other kinds of mosquito-borne diseases there are out there. And so you see, it's an epoxide. It has this cyclic three-membered ring ether. So the synthesis, the lab creation of this molecule was important, because if you have a stagnant pool of water, and if you spray this stuff in that stagnant pool of water, those larval mosquitoes are going to stay larval. They're not going to emerge as adults, and they're not going to go out and bite you. So this is another method of insect control that is probably preferable to spraying pesticide all over everything. Okay, so let's look at another example of a epoxide. This one's a pretty interesting one. A triptolide. And so we see these three epoxide moieties in this molecule. And this is a violent poison, but it's also a cancer therapeutic agent. And it's derived from Triptorginium wilfordi, whatever that is. And I wrote out its name in Chinese, and I will attempt to say it. Qi bu se tang. Translation: 7 steps, walk 7 steps and die vine. Meaning, if you eat the leaf of this plant and walk off in 7 paces, you're going to drop down dead. But this epoxide has the, this compound has this epoxide moiety in it, and this is used as a chemotherapeutic agent. So, epoxides are pretty interesting compounds. They occur in nature quite abundantly, and they're also interesting and useful laboratory chemicals. Okay, so first let's talk about how to create an epoxide in the laboratory. There are 2 ways. Both of them come from alkenes. Prep of epoxides. 2 ways. First way is called the Prilejaev reaction. Prilejaev reaction. You start with an alkene, right? Both of the methods for creating an epoxide that I'm going to talk about begin with alkenes as the starting material. And we know how to make an alkene, right? How do we make an alkene? E1 elimination of an alcohol. So we react an alkene with what is called a peroxy acid. So a peroxy acid has this Lewis structure, right? This is the peroxy acid. The usual solvent here is CH204, but I'm just not going to write that because that confuses people no end. And so the product is where that double bond used to be. Now there's, where the double bond used to be is now spanned by an epoxide, oxygen, and the organic junk we don't care about is a carboxylic acid. So it's actually an oxidation reaction where those carbon atoms of the alkene start life with 0 bonds to oxygen, but now they have 1 bond to oxygen each, so it's actually an oxidation reaction. So this Z here can be a lot of stuff. That's not the business end of the molecule. So this Z could be a hydrogen atom, it could be a methyl group, it could be a phenyl group, it could be all kinds of other fancy stuff, fancy phenyl groups. It could be a trifluoromethyl group. It could be a lot of stuff. That's not the business end of the molecule. The most popular peroxy acid, the most popular peroxy acid is called MCPBA, metachloroperoxybenzoic acid, which has this structure. So it's this peroxy acid with these, right? So that's MCPBA. So if you ever see MCPBA anywhere, that's just the most popular peroxy acid to use in this Prilejayev reaction. Okay, so up here, in this little box up here, I'm going to put an important bullet point for this reaction. And this is that the epoxide oxygen is delivered to the less hindered side of the original carbon-carbon double bond. And that's because of the mechanism, which we'll get into in a second. So this is the first way of making an epoxide. It's coming from an alkene. We're using a peroxy acid. But one of the things we have to remember is that that epoxide oxygen is going to end up where the alkene used to be, but it is going to be on the less hindered side of the alkene if it has one. Okay, so let's not talk about the mechanism yet. Let's just try some product prediction. Okay, so if we start with styrene and react that with MCP. Okay, I see questions coming through. I can't answer. I can't stop the lecture every time a question comes through. Let me hold your question and let me just get through this, and then I can address the question. I'm not ignoring you. I just can't just drop everything every time someone sends me a chat. Okay, so let's predict the product of this reaction here. Draw the structure of the product. All right. So what's going to happen here? MCPBA, that's the most popular peroxy acid. Tell me, does this alkene have a more hindered side and a less hindered side? Is it more difficult to approach from the front or from the back? It doesn't have a more hindered side or a less hindered side. So what you're going to get here is 50% of these molecules, the epoxide oxygen will be delivered to the front of the molecule. That means wedges. And 50% of the molecules will have that epoxide oxygen delivered to the back of the molecule. That means dashes. Okay, so tell me in the chat, how are these two molecules related? Are they constitutional isomers? Are they stereoisomers? How are they related? This is something you should have learned in Orgo 1. Yeah, these are enantiomers. They're non-superimposable mirror images, so I get a racemic mixture. of these two epoxides. And so that is going to happen when, this happens because this alkene doesn't have a more hindered side or a less hindered side. Okay, so let's try again. So here we have the alkene. We're going to react that this time with trifluoroacetic peracid, right? You see that 3 there? That's not a typo, right? Draw the structure of the product. So this reaction knocks out the carbon-carbon double bond, and it puts the epoxide oxygen where the carbon-carbon double bond used to be. But this guy, does he have a more hindered side or a less hindered side? He doesn't. So 50% of the molecules will react on the more hindered side, from the front, that's going to be wedges, and 50% of the molecules will react to place the epoxide oxygen on the less hindered side. Okay, tell me in the chat, how are these related? Oh, they're identical structures. This epoxide is meso, which is another term maybe you heard in Organic 1. So these are identical structures. If I take one of these and pancake flip it, it's the very same structure. So here we don't get a racemate. We don't get 2 different compounds. We get the same one. Okay, now you know what's coming now, right? Yeah, a molecule that has a more hindered side and a less hindered side. So here I'm going to use benzoic peracid. Draw the structure of the product. Does this alkene have a more hindered side and a less hindered side? Oh my heavens, yes. Tell me about that epoxide oxygen. Is it going to be on dashes or wedges? Tell me about that epoxide oxygen. Dashes or wedges? Yeah, it's going to be on dashes because the front of the molecule, the stick-up methyl group in this carbon 9 position, is going to make the top of the molecule of much more difficult approach. The front of the molecule is going to be more difficult to approach than the back of the molecule, so that epoxide oxygen is going to be delivered to the back of the molecule. Right, so this is one of the hallmarks of this reaction. We'll get into why this is in a second when we talk about the mechanism. Okay, let's try one more. No lecture of mine is complete without the witch's hat molecule, right? I love this thing. MCPBA, draw the structure of the product. And tell me about that epoxide oxygen. Is it going to be a hanging down stalactite, or is it going to be a pointy up stalagmite? Is that epoxide oxygen going to be dippy down, or is that epoxide oxygen going to be pointy up? Well, sure, it's going to be down, because this methyl group overhanging the double bond, that is going to impede the reaction from the top. And so the major product, or maybe I think the only product here, is going to be the dippy down stalactite epoxide, pointing down like that. Okay. So now let's talk about why this happens. That's the mechanism of the Prilejaev reaction. It's one step, but it's complicated. Mechanism. So here is the alkene. There's the alkene. And the peroxy acid hovers menacingly above the peroxy acid hovers menacingly above the alkene. Okay, so let's see, just bear with me for a second here. Because this is hard to draw, and I drew this out before class, and I don't want to screw up the drawing. Okay, so there's the alkene. The peroxy acid hovers menacingly above the alkene, but it hovers in that menacing way in just this orientation. So it's that oxygen at the end of the line of that peroxy acid that gets delivered, and every bond that is going to form and every bond that is going to break, this all happens in one step. That's why steric hindrance is important, because this is a huge, big, bulky molecule. The reaction is a one-step reaction. Every bond that is broken and every bond that is formed happens in one step. This is a big, huge molecule, so that's why it can only approach the alkene from the less hindered side. We can picture the transition state for this reaction. This double bond is going away, so I'm going to dot it like that. This carbon atom is forming a bond to that oxygen. Both of them are. So that's all dotted. The oxygen-hydrogen bond here, that is decomposing, and this hydrogen is being picked off by this oxygen, and this double bond is also decomposing like that. And then this single bond, this oxygen, is going to be promoted to a double bond, and this single bond is going away as well. So it's all a one-step mechanism. That's the transition state. The nickname for this reaction, for this mechanism, is the butterfly mechanism, right? I guess this is supposed to be the body of the butterfly here, and this is one of its wings, and this is one of its other wings here, right? So I don't like to ever show this mechanism to a student with arrow pushing, because it would just be a mess, right? I would have to do an arrow that way, an arrow this way, an arrow this way, an arrow this way. That's just not informative. So I prefer to show this butterfly, where all of these bonds are being broken and being created at the same time. There's the epoxide, and the other product of this reaction is the carboxylic acid. That's the organic junk we don't care about. Okay, so that's the first way of making an epoxide. All right, so let me see what's going on here in the chat, because I'm about to talk about the other one. Okay, there's nothing going on. Okay, so that's the first way of making an epoxide, this Prilejaev reaction. Next way of making an epoxide, let's see, did I put a number 1 earlier? Yeah. Next way, I put next way to make an epoxide, this is via a halohydrin, right? And this maybe was a reaction that you covered in Orgo 1. If you never heard of a halohydrin, doesn't matter. Just just going to go over all of this chemistry now. So this is the second way of making an epoxide using a halohydrin. Once again, it starts out with an alkene, the alkene reacts with either bromine, molecular chlorine, molecular bromine, or molecular iodine. So the alkene reacts with X2, right? And this could be either X could be Cl or Br or I. This is, the double bond is the nucleophile. It attacks the molecular bromine or iodine or chlorine. The bond snaps and we get an intermediate, which is called a cyclic halonium. Cl2, Br2, and I2, these are big, right? These are big atoms. These are big molecules. So this cyclic halonium ion is going to form on the less hindered side of the alkene if it has one, because Cl, Br, and I are huge, right? So we get cyclic halonium. Bullet point: on less hindered side of the original alkene. Okay, now this cyclic halonium reacts with water, right? The halonium is an electrophile. I know that because I see an atom with a positive charge on it. It's horribly strained. It's a three-membered ring. It's horribly strained. It's dying to be busted open, and it will be busted open by water, which is in the reaction mixture. Okay, so water, that's the nucleophile. The water is going to attack one of the cyclic halonium carbons, and this bond breaks. Okay, I'm about to switch slides here because I have many more steps to go. Everyone caught up? All right, so we get this intermediate. We get this intermediate, and this reaction where the water molecule has busted open that cyclic halonium. This we also have a couple of bullet points that we have to keep in mind for this, and that is that water attacks the more substituted carbon of the halonium. Right, that was this guy here, right? The water is going to attack the more substituted side of the halonium, and for steric reasons, it attacks anti to the X plus, and water attacks anti to X plus. Okay, so I'm laying a lot of stuff on you guys here, but we'll work some problems, we'll work some examples, and we'll solidify all of this. Okay, so remember that X minus that was produced in the first step? Remember this X minus that was produced in the first step? That comes back in, it functions as a base, and it's going to deprotonate this oxonium ion, and so we get the halohydrin, right? This is called the halohydrin. Okay, so now, so that is step one. All of that happens on Monday. On Tuesday, you come in and you're going to react the halohydrin with a base, and the base is going to remove the OH proton. So the best base to use here is sodium hydride, right? We saw him before when we were talking about in Williamson. And so that's a base that's going to deprotonate the alcohol of the halohydrin. And what I've set up here is the ideal situation for an SN2 intramolecular reaction. So this oxygen attacks this carbon, kicks out the leaving group, minus X minus, and finally and at last, there is our epoxide made in this other way using a halohydrin. Okay, now, big bullet point here, big bullet point for this reaction is that this two-step procedure delivers the epoxide oxygen to the more hindered side of the alkene. Epoxide oxygen on more hindered side of the original alkene, right? So that's why we need both of these reactions. That's why we can't just get by with the Prilejaev reaction, because we want control of whether to put that epoxide oxygen on the more hindered side or on the less hindered side. Okay, so this route to creation of an epoxide using a halohydrin, right? This is quite involved. So let's go through some examples. So let's start out with something that has a more hindered side just right off the bat. Okay, so we saw this molecule before, so let's go through all of the steps here, right? First step is going to be the reaction of this guy with some kind of halogen and water. All right, so now what are the steps? The steps are the double bond attacks the X of, it attacks that halogen. We get X minus off in the reaction mixture. And remember we said that for steric reasons, that cyclic halonium is going to form on the less hindered side of the original alkene. So there's our first important intermediate. And now what happens is the water insinuates itself, attacking the more substituted carbon, right? This bullet point here, water attacks the more substituted, and it also attacks in an anti-fashion. The X plus is huge. He's on dashes. The water is going to attack on a wedge. So there's water. This is the more substituted carbon here at 4 o'clock. This is the less substituted carbon here. So water attacks the more substituted carbon. It flings the halonium open. And so we have halide on a dash like that. And we have water on a wedge, like so. Okay, and then the X minus comes in. The X minus comes in, and it's going to deprotonate this oxonium. We get HX. And so at the end of step one, we have this. Okay, now step two. Step two is the treatment of this halohydrin with base. I want to use sodium hydride. And the sodium hydride ionizes that oxygen. It pulls off that proton. I have O minus on a wedge. I have X minus on a dash. It's all set up to do an intramolecular SN2. So X minus is the leaving group. And here's our final product. We see it's an epoxide, but the epoxide oxygen has been delivered to the more hindered side of the original alkene, right? So it's a complicated, involved mechanism, but and it's a two-step process. But what we need to recall about this process is just the double bond gets knocked out, and we get O epoxide oxygen on the more hindered side of the original alkene. Okay, so those are our two ways of making an epoxide. Now let's talk about the reactions of an epoxide. The epoxide is an electrophile. The epoxide is highly strained. It's dying to be busted open, and it will be attacked and opened up by nucleophiles. So the epoxide is an electrophile. Okay, so now we'll talk about reactions of epoxides. All right, so many epoxides, but not all of them, but many epoxides have what could be considered a more substituted carbon and a less substituted carbon. Not all epoxides are like this, but many are. So there's an epoxide, the carbon on the carbon on the left is the more substituted, the carbon on the right is the less substituted. Okay, so this is important to make this distinction because it turns out that this carbon here, the more substituted carbon, is the carbon that is attacked by nucleophiles under acidic conditions. Nukes in acid attack here. More substituted carbon. This is the less substituted carbon. Basic nucleophiles attack here. Okay, so let's go through some concrete examples of what you're going to be seeing above and below the arrows on a quiz so that you can recognize what is and what is not a basic nucleophile and what is not a nucleophile attacking in acid. Okay, so this is much simpler, so let's tackle this first. A nucleophile in acid means there's going to be a nucleophile there and acid will also be present. So many times you're going to see an H plus above and below the arrow when it's a nucleophile attacking an acid. So what are some of the common nucleophiles here that you would see? It would be something like water. That's a nucleophile, but we need acidic conditions. So above and below the arrow, you'll see H2O and H+. But did you know that H2O and H+ is the very same thing as H3O+? So if you see H3O+, that means water in acid. Okay, so what would be another concrete example? Well, maybe it could be an alcohol. That's a nucleophile, but you're going to see H+ above and below the arrow. It's a nucleophile attacking under acidic conditions. What would be another concrete example here? Maybe something like a carboxylic acid. But tell me, do you need to add acid to a carboxylic acid to make it an acid? No. So you're not going to see additional H+ there, right? So a carboxylic acid is acid already by itself. So no, it's already a nucleophile under acidic conditions, so you won't see H+ there. What about something like HCl? Do you have to add H+ to HCl to make it an acid? No. So you're not going to see additional H+. The acid is already built in. So these are some common examples of nucleophiles that will attack an epoxide under acidic conditions. Basic nucleophiles, this is a lot more complicated because a lot of people, unfortunately, even after 3 semesters of chemistry, have very tough time recognizing a base. What you're looking for most of the time is something that has a negative charge, right? Because a base is something that reacts with a proton. So bases are typically, not all the time. I'll give you an example of something that doesn't have a negative charge on it, but most of them do. So a base could be hydroxide. Is that a nucleophile? Oh my heavens, yes. Is it a base? Oh my heavens, yes. How do I know? That negative charge is a big tip-off. Another basic nucleophile could be alkoxide, right? This was the same nucleophile that we saw in the Williamson. Another basic nucleophile could be something like the alkynyl anion, right? I know that's a base because I see that negative charge on it. Another basic nucleophile could be, say, the amide anion, right? I know that's a base because it has a negative charge. So those are some concrete examples of basic nucleophiles. But we have an additional helper here with basic nucleophiles, because when we use a basic nucleophile, when we get into the mechanism of the reaction, just a second here, when we use a basic nucleophile, there will nearly always be a follow-up workup step with acid. So it's going to be these nucleophiles, then H3O+ workup. So that's an additional clue that we've opened up an epoxide with a basic nucleophile. Okay, so more bullet points for the reaction. Okay. Is that regardless of whether the nucleophile is an acid or a base, the nucleophile always attacks anti to the epoxide oxygen for steric reasons. And this happens whether it's a base or an acid. So the nucleophile always attacks anti to the epoxide oxygen. So in other words, even if the epoxide oxygen is on a wedge, the nucleophile is going to come in on a dash. If the epoxide oxygen is on the top of the molecule, the nucleophile is going to come in from the bottom of the molecule. Okay, another important bullet point for this reaction is to recognize that the product of opening an epoxide is always an alcohol. Where the carbon next to the alcoholic carbon has the remnant, what is left of the nucleophile. Okay. Whew. Put a lot of stuff. Let's talk about mechanism now. So did you get all that? Nucleophile attacks anti to the epoxide oxygen. Product is an alcohol where the carbon next to the alcoholic carbon has the remnant of the nucleophile. Okay, let's talk about mechanisms. First in acid. Mechanism in acid conditions. So there's our epoxide. I'm going to give it a more substituted side and a less substituted side. First step is protonation of the epoxide oxygen by acid. We get this oxonium ion. And now the nucleophile, I'm going to use, just demonstrate with methanol, right? That's a nucleophile in acid. The nucleophilic oxygen attacks the more substituted side, flinging the epoxide open, and it attacks anti. So the epoxide oxygen was up, the nucleophile came in from the bottom for steric reasons. And now the reaction is catalyzed by acid. A proton got everything going at the beginning, but the last step of the mechanism is the deprotonation of this oxonium ion. And here is our final product of opening the epoxide under acidic conditions using methanol. And notice that the product is an alcohol, where the carbon next to the alcoholic carbon has the remnant, what is left of the nucleophile. Okay, so that's the mechanism for opening the epoxide under acidic conditions. Essentially, it's driven by the desire of the epoxide to be opened up to relieve ring strain. Okay, so that's the mechanism in acid. All right, so now let's look at the mechanism in base. A lot simpler. So here's our epoxide, same one as we did before. It has a more substituted side and a less substituted side. And instead of HOCH3, I'm going to open the epoxide up with this basic nucleophile, right? How do I know that it's basic? Well, one way I know is that it has that negative charge. and the nucleophile attacks the less substituted side. It flings the epoxide open. It attacks anti. And so, you know, that's it. That's it as far as opening the epoxide. Now, I said before, and I'll remind you that what I said is that after the basic nucleophile is used, then we nearly always have a workup step. And that workup step with aqueous acid, that just is going to put the negative, it's going to douse this negative charge and convert that into OH. So in a totally separate step, H3O plus, separate step. That H3O plus isn't in there at the beginning. Separate step. The H3O plus simply protonates that OH, and so that would be our product in base. So once again, it's an alcohol where the carbon next to the alcoholic carbon has the remnant, what is left of the nucleophile. And so let's just compare what happened in acid compared to what happened in base. Well, in base, we got that. And in acid, we got this, right? This is what we got in when we opened the nucleophile in acidic conditions. So that's very nice for us organic chemists, because this is telling us if we want OH over here, we open in base. If we want OH over here, we open in acid. So these two procedures offer this complementarity with control. Okay. So let's do a bunch of problems, right? Only have about 6 or 7 minutes. Let's do a bunch of problems. Okay. Let's go with this guy. One of my favorite molecules. Wedge, double bond. Okay. First step, MCPBA. Second step, ethoxide. Third step, H3O plus. And you see the layout of this problem? For your quiz next week, problems like this, 100% guaranteed. Product prediction. Draw the structure of the product. Okay, so what happens in step 1? Step 1 is the creation of the epoxide using a peroxy acid, the most popular peroxy acid, MCPBA. That is going to put the epoxide oxygen on the less hindered side. So obviously a skill that you want to work on is being able to detect the less hindered and the more hindered side of an alkene. Tell me in the chat, what about that epoxide oxygen at the end of step 1? What about that epoxide oxygen? Dashes or wedges? That epoxide oxygen at the end of step 1, dashes or wedges? Yeah, it's going to be dashes, because the front of this molecule has this huge dimethyl cyclopropyl moiety. the back of the molecule is defended by these teeny tiny hydrogens. So at the end of step 1, the epoxide that we get is going to have the epoxide oxygen delivered to the less hindered side, dashes. Okay, now, step 2. Are you attacking the epoxide under acidic conditions, or is it a basic nucleophile? Oh, it's a basic nucleophile, right? How do you know? Well, one way you know is that oxygen atom, that's the nucleophile in step 2, that has a negative charge on it. So which carbon is going to be attacked? The 2 o'clock carbon or the 4 o'clock carbon? Which carbon is going to be attacked? The 2 o'clock carbon or the 4 o'clock carbon? It's going to be the 4 o'clock carbon, which is the less substituted carbon. And tell me about how this nucleophile is going to attack. Is this oxygen atom of the attacking nucleophile, is he going to be on a dash or on a wedge? This is the carbon that's going to be attacked because that's a basic nucleophile. Is this oxygen going to be on a dash or on a wedge? Oh, it's going to be on a wedge because the nucleophile has to come in anti to the epoxide oxygen. So at the end of step 2, we have dash, 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 wedge, wedge, wedge. The nucleophile attacked the less substituted carbon. It does so anti to the pre-existing epoxide oxygen. And so at the end of step 2, we have this. Now, in step 3 is just a workup step, which normally follows attack of the epoxide by a base. And all step 3 does is it puts the epoxide, it puts that O minus, protonates that O minus. And so now finally and at last, and notice I did this whole problem just based on bullet points. If I had to write out the mechanism for each of these steps, I could have done that. But I got to the final product just keeping in mind what I like to present as bullet points for the reaction. Okay, so time has elapsed for now. I still have a couple of different things to talk about, but I'm going to have to slop over into Monday. Over the weekend, I'll be publishing a study guide to the quiz. And so, but I think I've talked about 95% of the stuff that's going to be on the quiz.